Hey everyone, we're going to look at the next lesson here in the exponential unit. And so just comparing exponential to all the other types of relations. We've been kind of doing that all the way along anyways, but good to have a little extra practice with it, so it doesn't hurt. So just going back in time to grade 9, this is what a lot of the course is about. Where if you had your first differences were constant, then you know that it's a linear situation. Makes a straight line, graph looks like that. And then in grade 10, and then reviewed in this class as well, we have the second differences. If they're constant, then you know it's quadratic, and of course it has the key quadratic shape where you've got your 1, 3, 5 step pattern, right? So a 1, 3, and then 5 step pattern, to the 9 here. So 1, 3, 5, and so on. Anyways, just review some of that stuff. And then the new stuff from this class, right? The key for exponential relationships is that we have a common growth factor, right? And we have a slow growth and a fast growth. Obviously, we could have had an exponential decay version as well, right? If we had a 0-point number in here, then it would have been this kind of graph. It would have been exponential decay. So add on green here, or decay. All right, so that's just what we've seen, right? And so if we're looking at an example here, just be able to do this kind of thing where you're going to look and see what the first differences are. And so this is +2, +2, +2, +2. And so because of that, we know it's linear. So we have constant first differences. So that means it's linear. So the equation we know to do with that is y equals mx plus b. And I was supposed to put key features down here was constant first differences. So that's how I had it organized, but I forgot here. So there we go. So constant first differences, therefore it's linear, of course. And then the second one, if we did our first differences, we'd have down 3, down 1, up 3. Then our second differences, if we're going from 1 to 3, you can tell it was up 2. From -1 to 1 is up 2. From -3 to 1 is up 2. Right? They're all up 2. So we have constant second differences. Therefore, it is a quadratic. And if we were graphing, I guess I should have gone back and graphed this stuff too here, right? So 0, -2. Sorry, -2, 0, right? -2, 0, -1, 2, 0, 4, and so on. So that's about all I can graph for that one. From the graph, we would have had to go to -3 and so on, but for now, that's all we had. So I'll just graph that thing as it was. This one here, if we graphed it, we'd have our 0, 0, our 1, 1, our -1, 1, our 2, 4, and so on. So you probably recognize that, hopefully recognize that pattern and know that it's literally just y equals x squared. And then in this one here, if you tried first and second differences, you'd find they weren't constant. So instead, we're looking at the constant multiple, right? So what's the constant multiple going from each step? Some of them are easier than others to see. So let's look at the work at it backwards, like I did with the second differences even actually. Easy to see that that's multiplied by 2. Half times 2 is that. Half of a quarter is a half, and so on. So these are all multiplied by 2. So these ones have constant multiples. And so they are exponential. rate is exponential, however you want to word it. Looking at the graph, we got our 0 and a 0.5. And we have a 1 and a 1. And a 2 and a 2. And on the other end, we had a 0.2 or 0.25, 0.125, and so on, right? So it's going to be a graph like this. Okay. Yeah. So you probably could recognize that that graph's going to be basically this. It's a regular. We have the 2 to the power of x, certainly. Then in order to get a 0.5 start here, we have to have a 0.5 in there. So I will need that a little bit. Well, I can probably squeak it in there. So 0.5 from this starting value. There we go. So backtracking here, I guess the equation, we might have just said, it's a, b to the x, certainly, but number-wise, we can actually see what those numbers are. Generic equation here was all the different forms, right? ax squared plus bx plus c. The numerical actual versions we were able to do, I didn't do the lines, we can go back to that. If we had y equals the slope, so that's the 2, right? That is your slope. That's your 2x. And then your y-intercept in this case was a 4. So kind of jumped around a little bit there, but we can actually get the number version of the equations as well. It's just knowing the general forms. Just forgot to do it when I was looking at some of them. So yeah, so basically be able to classify each of these things, right? So if it's a y equals mx plus b, obviously it's going to be number x plus number and so on. It's going to be obvious that it's linear. If we had an ax squared plus bx plus c, numbers being the a, b's, and c's, obviously it's quadratic. Other versions of that, we have the vertex form and the factored form. And so numbers would be in for the letters in each case. Letters other than x and y, that is. And then in this one, that's obviously exponential, right? So we got number times number to the power of x. That's an exponential. Literally because there is an exponent, right? Right there. The variable, I should say, is in the exponent. There's an exponent in quadratic, right? But it's not the variable. So when you're looking at these equations, if this was in random order here, you'd have to be able to recognize that this is in a y equals mx plus b format, and so it's a line, it's linear. And this one here, there's a power of 2, and so that's a quadratic. And this one has the exponent is the x, and so it's exponential. Things to know and be able to identify and watch for and so on. So moving on here to a table of values. So if you're looking at first differences, second differences, and common multiples, that's your key, right? So first differences and second differences and common multiples. You might choose which one you do first based on what things look like. But if you're not sure, you just have to check at random and see, right? So if you look here at the first differences, we get a difference of, this is a 5.4, take away a 3.1 in case it's not obvious how you would do that. It gives you a difference of 2.3. And this difference also ends up being 2.3. And this one also 2.3 and so on. Good thing because I'm taking up too much space here. Right? So 2.3, because they're all constant, it means it's linear. So constant first difference, and it means that it's linear. And if we do our first differences and second differences and so on in a case, you'd find in this case that they don't end up constant. So you would just try it though, right? You'd be like, first differences, get your numbers so you can tell that's a difference of down by 1. No, up by 1, sorry. And then 3.5 to 4.9 would be 1.4. And then that one there, 6.86, take away 4.9. I better just do that one. 6.86, take away 4.9. 1.96. And then 9.6, take away 9.6, take away 6.86, 2.74. I could have stopped a long time ago as far as this goes. If it's not constant, therefore not linear. But we'll need those numbers anyways to keep going to get the other stuff, right? I was supposed to say linear. I'll fix that up. A little bit better at least anyways. Oof, not really. Let me try again. Jeez. Linear. Because my L looked like my L was too short. It looked like an I. Anyways, so not linear. And then we could do the second differences, which you can tell here would be like plus 0.4 and plus 0.56 and plus, whatever that one is. I think we can tell it's not constant as well. So it's not quadratic. So it's kind of a pain if you're not sure, right? You just have to keep checking and so on and see what happens. And eventually maybe you start to look at the common multiples. Just recognize, of course, the common multiple has to be on the original numbers, right? So the 3.5 divided by the 2.5 gives us 3.5 divided by 2.5 gives us a 1.4. So is there a common multiple? And so we got times, what did I say it was, 1.4? Yeah, 1.4. And then 4.9 divided by 3.5. 1.4 again, so it's a good sign, right? So if you kept going here and found these are all 1.4, then with confidence you can say, oh, well, that thing is exponential. We have a common difference, and so it is exponential. All right, so I'll just leave the part C there. Obviously, we've done enough there that you can carry that process out for the other one. And if we're looking at a graph and maybe getting a table of values from a graph, or looking at these two graphs, they certainly look like they could be exponential. So determine if they are. If one is not, determine what type it is, and so on. If you look here, we end up with multiples. So basically, we're looking for CM common multiples, right? This one ends up being times 1.4 times 2.4. So right away, we're like, if we keep going if you want, but it's not exponential. So I guess our next step would be to determine what it really is. So maybe we'd backtrack and do the differences. So we'd see here, this is first difference of what? 0.2, and then 0.7, no, 3.8 plus 0.8, and then plus 1, and then plus 2, and then, is that right? 0.7, 0.2, 1.5, 0.3 brings us to 1, so 0.8, 1. Yeah, looks good. And then it's over to make some room. Second differences, possibly. This one is plus 0.6. This one's only plus 0.2. I feel like I might have done something wrong here, but plus 1, so it's not bad either. So it's not quadratic, not linear. Basically, it's none of those. It was set up as to determine which type it is, which makes me think that maybe it is a certain type, but that's not working out unless I made a mistake somewhere. Anyways, I had this worked out. It's like it's not a common multiple, but same kind of analysis on this one, right? You look for common multiples and so on, see what you get. I think part of the problem is estimating from the graph. So sometimes, like this one here, for example, if it literally is estimating from the graph, then you might not have perfect numbers. So if this is if it's a multiple of 1.2 and multiply at 1.25, and this one's multiplied by 1.4, it might actually be true, right? It might be a common multiple and just based on estimates. So it's like an approximate common multiple. So what you do there is you just get more numbers, right? And or try to approximate the numbers more carefully or whatever. Okay, so it seems like the red one could be exponential, right? Where it'd be like this kind of pattern here and up and up and up and so on. So this one looks like it could be. But if it's data from an experiment, you certainly have to tolerate some variation in the numbers. So anyways, that's the idea. We know what we're looking for at least anyways, right? There was an example here, which is exponential. If they're exponential and justify your answers. So this one probably works out a little bit better, but so this is the decay curve. Decay constants are the constant, yeah, exactly 0.8, 0.8, 0.8. Not necessarily going to have that in a real life situation, right? So even here, I'd still be wondering. I'd be wondering if it's just approximate data. In which case, it maybe you collect some more, and it could be exponential in that case even. I would say the numbers are pretty close there, right? They're all in the same ballpark. Yeah, I wouldn't rule that one out as a science person. If you're just looking directly at the mathematical relationship, then, oh yeah, they're not constant. But obviously when you're measuring things, it's not necessarily going to be perfect numbers all the time. Okay, so I don't really like that textbook example. That's honestly why I'm including it, so that I can make that statement where it's like saying, okay, well, in an experiment situation, you can't expect 0.80 exactly, and that's the only way you're going to conclude that there's exponential decay or growth going on. Okay. All right, so as usual, first page, practice questions. To submit, if you have questions, let me know either by email or in the discussion post. So that's all for now. Thanks for watching, and don't forget to like and subscribe, as they say. All right, talk to you later.